Okay, so many of you are familiar with the ISA EC50 training. You gotta love the some of the pictures here. So we're talking about human beings doing things the wrong way and how we deal with that. It is an important topic, but the big picture message of this webinar is human failure is going to be a big driver of industrial disasters. Always has been, always will be. But fixing the problem can't happen by just, putting more numbers into spreadsheets, more numbers of dubious origin. So, yeah, every once in a while, you might end up seeing something like this. I can't imagine that this was done by accident. Somebody had to have done this on purpose. But for those of you that are in the know, the chemical process is supposed to go in here in the manifold. And these connections are not for the process. Those connections are for the electrical wiring. So your electrical conduits. So if you pipe your flow through the electronics of your transmitter, not going to work so well. Now, if this happens, do we really want to run our calculations to calculate the probability that somebody installs it like this? Is there any benefit to that whatsoever? The answer is a solid no. Calculating the probability that somebody doesn't install something correctly is not going to be helpful to us. As a matter of fact, I'm going to go on to show you through the rest of this webinar that trying to include the frequency or probability of human error in our SIL verification calculations not only is not going to be helpful, it's actually going to get us to do the wrong thing. It's going to trick us into making a bad situation even worse. Okay, so let's get to that. So this is, I just wanted to kind of show you this picture. And the key is that in the training class, we're saying that the mechanism that we're going to use to detect this failure is not online diagnostics. It's not a proof test. It's the commissioning process. The commissioning process should be one human being checking the work of another human being and saying, hey, that's not how you install a transmitter. You don't pipe the process through the electronics. So that didn't show up in the PFD calculation. That showed up in the commissioning, where we are back checking other people's work. And there's going to be a strong stress that says human failures need to be detected by other administrative controls, other people checking the work. That's all going to be clause 5, and I'll get back into clause 5 in a second. Okay, so validation, functional safety assessment, we're going to talk about a little bit more. There's a slide that I'm getting to here, if you bear with me for a second. Now, at the end of the EC50 class, we have this last slide that talks about the impact of systematic failures, of functional failures. So a systematic failure is something that's different than what we're going to do our SIL calcs on. We're doing our SIL calcs on random failures. Random hardware failures is what we're focused on when we run our SIL verification calculations. But we have to acknowledge that there is going to be an impact to a systematic failure. So a random failure is something that just kind of happens for an unknowable reason at an unknowable time. A systematic failure is something that's built in by design. It will always happen under the same circumstances every time it's tried. So it's kind of a design error. And generally, those design errors are going to be based on human beings doing things the wrong way. So, what is the impact? So, think about failure. How often um, do you make mistakes? How often do beings make mistakes doing routine activities? I could tell you it's very high. Because as a senior person in the company, I routinely am responsible for doing verification, checking other people's work, whether it's a cell verification calculation or one of my assistants putting together a proposal. And they will routinely make errors. So yeah, you did a proposal for a gas mapping study when they asked for a fire mapping study is an example of a systematic failure that resulted in the wrong proposal. Or you chose the wrong device out of the pick list and your calculation is wrong. So how often do you make these kinds of mistakes? 1 in 100, 1 in 10, uh, worse than that? How often have you found something installed correctly? So I don't know if anybody noticed, but if you look at the web page that announced this webinar, we have this picture shown. So it always is entertaining for me to, and again, I have been told that people have actually seen this in the wild. So you're looking at a thermal well, and the purpose of a thermal well is to project into the process uh, and give you a location inside the process where you could stick your thermocouple to make a better measurement. Well, the thermocouple is on the outside. This point should be inside the pipe. So we kind of bolted this thing on backwards from how it should be bolted on. And again, I would say, somebody did this on purpose just to take a picture, but people have told me, no. We have seen people actually make this mistake. So how often are things installed incorrectly? In my previous life at UOP and even at Conexus, I've assisted in commissioning. I've assisted in SATs. Not one time have I done a commissioning and everything was installed correctly. Not once. So is it 10% of the instruments? 1% of the instruments? What's the probability that the commissioning will catch the fact that it was installed incorrectly? And how often have you found something engineered incorrectly? So looking at this last picture down at the bottom here, this is kind of, instrument engineering 101. Well, maybe not 101. We're measuring the flow by getting the differential pressure upstream and downstream of an orifice plate. So we can correlate that differential pressure to the flow rate based on the temperature and the properties of the fluid that's flowing. Now, if you didn't notice what's wrong with this picture down at the bottom, in order for those correlations that convert a differential pressure into a flow rate to be true, there has to be a certain amount of straight run piping upstream of the orifice and downstream of the orifice. So if you put an elbow right at the outlet of that orifice plate, you're not going to be able to correctly measure. There's going to be an error, a systematic error in your flow measurement because it was just engineered incorrectly. So, I mean, what's the probability that somebody made this mistake? What's the probability that it got through all the design reviews, including commissioning? Back when I was at UOP, this would would not get through because I know that this is something I would check on my installation drawings. But hey, not everybody is the highest quality engineer. So there are mistakes that you make just doing routine activities, mistakes in installation, mistakes in design. Now, if we say that every activity has a probability of failure of 0.01, how many activities went into the design of your safety instrumented system? Now, the probability of doing something wrong is a strong function of what you're doing. So saying that a human error probability of 1 in 1,000 is optimistic, well, that's not necessarily true. So the probability that I will be able to bounce a quarter off of this table and have it land in my coffee cup, 1 in 1,000 would be optimistic. But if you look at another activity, like you're in your car and you approach an intersection that has a red light, what is the probability that you misinterpret the red light and just go through the intersection? I would say that 0.001 is not just pessimistic, it's very pessimistic. I mean, if it was actually 0.001 for misjudging a red light, pretty much every intersection in the world would have an accident at least once a day. I mean, 1,000 cars going through an intersection in a day? Yeah. I digress. But if we use those numbers, then based on human factors, we really shouldn't say that SIL 3 is even possible. So SIL 2 could kind of be a theoretical limit of a system just based on the fact that, well, some human's going to screw this up, which is another one of those reasons why, if your LOPA says you need a SIL 4, that's pretty much a hard no for almost every organization I'm aware of. To try to like put all your eggs into that one SIL 4 system seems like a crazy thing to do. But a lot of organizations are also, when they get to SIL 3, they're like, I don't know about that. So, I mean, that kind of SIL 2 limitation is kind of matches up with gut feel, saying that, I don't really want to try to design a system that's even SIL 3, let alone SIL 4. Now, but where do we account for this? Okay, so I'm going to close out of this EC50 training class. If you haven't taken EC50, it's a great class. I highly recommend it. But I'm going to jump out of my PowerPoint slides here, and I am going to go into the standard and start looking at where do we talk about human failures and how they need to be addressed, where do they need to be accounted for. So I am going to go to clause 11. Why am I going to go to clause 11? Because clause 11 talks about the detailed design of the safety instrumented system. As anyone who's taken a training class with me knows, clause 11 is my favorite. It has a lot of the prescriptive cookbook requirements for how to design your safety instrumented system. So things like manual means, put my magic pen there, manual means to bring a safety instrumented function to its safe state. This clause has nothing to do with achieving the SIL target. Clause 11.2.10 talks about shared devices and provides, requirements there. So there's a lot of this stuff. But also in clause 11, we're going to go to clause 11.9. And clause 11.9, what I'm going to show you is the current state of clause 11.9. But just a few weeks ago, I was at the IEC 61511 committee meeting. So if you don't like what's in the standard, I can be definitely partially to blame for that because I'm on the committee. So we're making changes to this. Clause 11.9 is called quantification of random failure. That's a very uh, ambiguous term. If you wanted to be a little bit more precise, 11.9 is the SIL verification clause. So 11.9 explains not exactly how to perform a SIL verification calculation, but what you want to include in that SIL verification calculation. And this is one of the clauses that we took a deep dive on in the IEC 615 committee or 61511 committee meetings just a few weeks ago to try to clarify things and try to move clauses where they actually belong. So here we are listing out the requirements for the SIL verification calculation. So let's go into them, and we're going to have a very specific focus on today. The topic du jour is human failure. So how does human failure get addressed by the standard, and specifically how are we treating it in this SIL verification clause? Well, let me tell you, starting out, human failure is systematic. So right out of the gate, right in the darn title, right in the title of the section, SIL verification is the quantification of random failures. And a little bit later, we're going to stress that it's random hardware failures is what we're worried about. So the primary takeaway from this is do not include systematic failures and systematic human failures in your SIL verification calculations. Do not do it. The standard tells you not to do it. Only include random hardware failures. Do not include human failures in here. So that's the big key takeaway. Now I'm going to dive back down into some of the subtleties. So right out of the gate, SIL verification is about quantification of random hardware failures. It says so right in the title of 11.9. Okay, 11.9.1 starts out by saying the calculated failure measure of each SIF. Well, actually, we do SIL verification to see if we achieved our SIL target. Why didn't the standard just say SIL target? Instead of saying SIL target, it says calculated failure measure. Well, your calculated failure measure can be a bunch of different things, and the standard acknowledges that it can be a bunch of different things. So some of you are going to say, I'm trying to achieve SIL 1 with a minimum risk reduction factor of 30. So my calculated failure measure is a risk reduction factor of 30, not just the SIL 1. Okay? And so you might also say, well, my calculated failure measure is a PFD of 0.05, where, 0.1 is SIL 1, 0.01 is SIL 2. I might be looking for something in the middle. So the standard allows you to have different calculated failure measures than just that order of magnitude SIL target. Furthermore, depending on the mode of operation, the calculated failure measure might be a risk reduction factor if you're in the low demand mode of operation, but if you're in high demand mode or continuous mode, your calculated failure measure might be a frequency. So we're being deliberate, I don't want to say vague, but we're being very inclusive in our terminology because calculated failure measure, maybe it's a frequency, maybe it's a probability, maybe it's a SIL number, whatever it is, we need to achieve it. Okay, so we're trying to determine whether or not we achieved our calculated failure measure. So the calculated failure measure must be better than the target measure as it was specified in the SRS. Our SRS is telling us what the SIL targets for all our functions are. This shall be determined by calculation. So the standard right out of the gate says it's having a cookie cutter cookbook is not okay. You pick a SIL and then you quantitatively verify you achieve that via calculation, not an option. Okay, so that's 1191 says for every function I have, I'm going to quantitatively, by calculation, verify that I achieved my target. That's clause 1191. 1192 says, given that I need to do this calculation, what do I need to include in my calculation? So 11.9.2 is giving you a list of things you need to include, but it doesn't actually tell you how to do the calculation. It doesn't talk about unavailability, unreliability, whether you're in the constant failure rate regime. There's a lot of stuff that goes into these calculations that's outside the scope of the standard that's best practice. What we're going to talk about now is what's included in the standard, which doesn't give you a mechanism to perform the calculation. It just tells you what you need to consider. So item number 1 is, what is my architecture? So 1 out of 1, 1 out of 2, 2 out of 3, 2 out of 2, those are different architectures, and different architectures are going to have different probabilities of failure, risk reduction factors associated with them. So you need to think about your voting arrangement. It's pretty straightforward. Items B, C, and D are all failure rates. So item B basically says I need to consider lambda DD. So the failure rate due to random hardware failures that would contribute to a dangerous failure that are detected. Key phrase, random hardware failures, not systematic human failures, random hardware failures. Lambda DD should not include the frequency at which a human messes something up. It should only include the random hardware failures. As we move along, we're going to continue. All the failure rates that we're putting into our equations are random hardware failures. So for item C, random hardware failures, we're looking at this is going to be lambda du is going to be item C. So dangerous detected failures that are undetected by diagnostics but are detected by proof tests. And then the D is lambda DN, the never detected failures. So they're not detected by diagnostics and they're not detected by the proof tests either. So those lambdas I need, and those lambdas should not include human failure. They should only include random hardware failure. It says so 3 times, in addition to the random failure right up here in the title. Okay. Now, what else do you need to consider? I've got great news. So this clause E said I need to consider the susceptibility of the SIS to failures that are caused by the proof test themselves. So basically, if I need to put something in bypass in order to test the device, but then I forget to take it out of bypass, I have my proof test has caused a failure in my SIS. Or, another one to think about, especially, with regards to never detected failures. If I test my float level by sticking a 2x4 into my vessel and lifting it up, there's a chance that I could break the device with my 2x4. Okay, so does anybody actually do this? Has anybody included a lambda, my technician poked a hole in the float with the 2x4? I have never seen anyone actually include this in a cell verification calculation. And guess what? The standards committee said, no, we're not doing this because, again, this is not a random hardware failure. So the next version of IEC 61511, clause G, is going to go away. So hopefully that gives everyone a little bit of a sigh of relief. You're not going to need to think about that anymore. Okay. Item H talks about proof test coverage for the manual proof test. So what's the probability I'm actually going to be able to detect a failure when I do my tests? I need to think about repair times. This clause J is going to go away. The reason it's going to go away is not that you don't need to be concerned about communication processes, but this is, item J is a subset of B, C, and D. Communication devices have lambda DD, lambda DU, and lambda DN that you need to include in your calculation. So this is just kind of redundant language, which is why the next version of 1511, that clause is going to go away. The utilities, this clause is also going to go away, not because utilities are unimportant, especially if you have energized to trip. Utilities are important, but it's still just another subset of lambda D, or lambda S, actually, probably, for de-energized to trip systems. So those clauses are going to go away. Just more for clarification than anything. The other clause that's going to go away is the topic of today's discussion, this guy right here. So what have we talked about so far? The title of the section is quantification of random failures. For our clauses that tell us what failure rates we need to put into our equations, we specifically say random hardware failures. So we've been beating you about the head and neck that says we're talking about random hardware failures, not human beings, not human failures. And then we come back and we put clause K in, which says, well, when you're doing your SIL calc, you need to consider the estimated likelihood that operator response will cause a dangerous failure of the sys. Timeout. What just happened here? You just spent umpteen clauses telling me I'm only worried about random hardware failures. Now I get down here to K, and you're telling me again that I need to include the human being in this. Yes and no. Okay, so let's clarify this. This is one of those things that a lot of people read this clause and said, okay, I need to consider the probability of human failure when I'm running my calculations. Yes and no. This is different. So now I'm going to need to back up to a question of definitions. What is a safety instrumented function? All right, so I'm going to back up now to the definitions section, but just giving you a little bit of a preview. The IEC 61511 committee in our last meeting said we are striking this also. This is going to go away. So that's pretty interesting. So now let's go back to the definition and see where this comes from. So I got a question in the chat, and I think it's probably going to be relevant to this. So could you explain how a diagnostic test have a human interface? Okay, I will come back to that in a second. Yeah, the diagnostics in the humans. Okay, so let me go to definition. So what I'm going to talk about here is, so definitions are where? Everyone? Anyone? Clause 3? I'm going to go to the definition of a safety instrumented system. So everybody knows that clause 3 is semi-alphabetic. It's not exactly alphabetic, but it's semi-alphabetic. So I want to know, what is a safety instrumented system? Okay, so a safety instrumented function, let's start there. A safety instrumented function is what we're assigning a SIL target to, and we're doing the quantification of its performance. And a safety instrumented function, you gotta love these definitions, is a safety function to be implemented by a safety instrumented system. Clear as mud. Okay, so well, now I need to know, well, what is a safety function and what is a safety instrumented system? Okay, a safety instrumented system is defined as an instrumented system used to implement one or more SIFs. Well, that's real helpful. Okay, so maybe I really need to focus on this safety function. So a safety function is a function implemented by one or more protection layers. Whoa, how confusing is that? Which is intended to achieve or maintain a safe state of a process with respect to a hazardous event. This, okay, I'm showing you all this, and I'm intentionally trying to confuse you. And the one thing I'm going to do to confuse you even more is point to this note 1 to the definition of a safety instrumented system, which says an SIS is any combination of sensor, logic solver, and final element. Now, if you get a room of SIS professionals together, we are all going to agree that a safety instrumented function that I'm going to assign a SIL target to, that I'm going to design in accordance with 61511, is a completely automatic loop. I have a sensor that measures a process variable, a PLC that does logic based on that measurement, and it takes an action on a field final element to move the process to a safe state. But that common understanding of almost everyone of what a safety instrumented function is not what's actually in the standard. The standard says that a safety instrumented function can be any combination. So now, if I have, okay, here's my pipe, here's my pressure transmitter, and here is my valve. And if the pressure goes high, I want to close the valve. That's my safety function. Now, normally, you would wire your pressure transmitter to a logic solver that would do a PSH. And if the PSH fires off, I'm going to automatically close that valve. But what if instead I'm going to have my, let me make this a little bigger. What if instead I wired my pressure transmitter to a pressure alarm high? So let's make it a switch high instead of a transmitter high. So now I'm wiring to a alarm, and then I have an operator who is obviously wearing their safety glasses, is going to see that that alarm was activated, and that operator is going to mash a push button. Is this a safety instrumented function? Well, I would say no. I would design this part to ISA S18. I would design this part to API 560. Is that the valve standard? There are other standards for push buttons. There are other standards for valves. There are other standards for alarms that you would design to. But even though I wouldn't consider this a safety instrumented function, almost if you get a room of SIS experts together, they wouldn't call this a safety instrumented function. When we were talking about this in the ISA 18 or IEC 61511 committee, all the committee members said, gee, I wouldn't consider this a safety instrumented function. But if you look at the definition, well, I've got a switch, I've got an alarm, I've got a push button, I've got a valve. That combination, that's a combination of equipment that's performing a safety function. So there are people out there who will treat this like a safety instrumented function. If you're going to treat this, and I don't recommend it, if you're going to treat this like a safety instrumented function, then guess what? That guy right there is your logic solver. And you need to include that person as the logic solver in your SIL verification calculation. Let me move back up now to clause 11.9 and look at this again. So why is that clause K there? How has it been misinterpreted? And how should it actually be used? All right, clause 11.9, 2K. The estimated likelihood that operator response would cause a dangerous failure of the SIS. What we mean here is if you're going to include a human being as a logic solver, the probability of that human failing needs to be part of your SIL verification calculation. Okay, everybody on the 61511 committee just said, yeah, we're going to get rid of this clause because we don't think that you should be including a human being in a SIL anything loop because we don't believe that a human being is suitable even for SIL 1. If human being is your logic solver, we don't think that you're going to get a risk reduction factor of 10, which is not SIL 1. 10.1 is SIL 1. You know, it's got to be greater than 10, not equal to 10. Equal to 10 is a LIPL, low integrity protection layer. Basically, we're going to get rid of this, but just kind of giving you the historical perspective, this was here to accommodate using a human being as a logic solver. Historically, we're going to whack it. So 1511 committee said, yeah, let's whack this one. But that clause has created a cottage industry in saying, well, I'm going to include human failure in my SIL verification calculations. Don't do that. I mean, you can go and you can see examples of human failure being included in your SIL verification calculations. I'm going to beg you not to do it. The standard basically tells you you shouldn't do it. And I'm going to now go into the explanation of why including human failure in your calculation not only is not going to be helpful, it's going to be counterproductive. It's going to tell you to do things that are actually going to increase the PFD, even though it looks like you're decreasing the PFD. So in order to do that, let me bring up my equations sheet. Bear with me. So for those of you that are familiar, this is the student note set for EC50. If I go into the student note set for EC50, at the very end or toward the very end, we're going to have a list of all of our equations. So let's say, once again, let me draw out our archetype safety instrumented function. I have a pressure transmitter, and I am going into an SIS logic solver, and then I am going to close a valve if the pressure gets too high. Okay, in order to run my SIL verification calculation, what I'm going to do is I'm going to determine what formula I'm going to use. And then for that formula, I am going to determine which terms are appropriate. So let's just make life easy and say, okay, let's assume this transmitter has no diagnostic, so this term goes to 0. Let's assume right now that we have perfect testing. So DN is going to go to 0. Let's assume we're only doing offline testing during the turnaround, so the online testing term is going to go to 0. Now I've got my lambda DU multiplied by test interval over 2. That's going to be my PFD for my transmitter and my valve. So when I get my lambda DU, my lambda DU is going to come from some sort of database that talks about failures of the transmitter. So the random hardware failures are what you're looking at in your databases. And let's just say that lambda DU is going to be something like 1 over 50. And then you're going to plug in your numbers to run your calculation. So if you test once a year, it'll be 1 over 50 times 1 divided by 2, 1 over 100. That's going to get me to a PFD of, if it's 1 year, 0.01. Okay, let's say we needed to achieve SIL 2. Now, granted, when you see SIL 2, you're probably thinking I need more devices, which you probably would need to get to SIL 2, but let's just look at this one device for a second. This lambda DU was random hardware failures. Now, if I looked at clause K and I said, oh, I need to include the probability or the frequency of failure associated with human interactions. How do humans interact with this transmitter? So what are the different ways that a human being could have screwed this transmitter up? So one is engineering failure. So I picked a measurement device that's not actually able to measure the device properly. Number 2 could be an installation failure. So I might have installed that pressure transmitter in a location where it's not actually going to detect that the hazard's present. Maybe I installed it upstream of a T when I should have installed it downstream of a T. So that's an installation. Well, you could also call that an engineering failure. 3, calibration failure. So I've got a technician who's going to go out and they're going to calibrate all my transmitters on a regular basis. And if they mess up the calibration, there's a failure mode where it wouldn't read as high of a pressure as is actually occurring in the process. That would be a dangerous failure. So there's, a rate at which you make failures. So there's going to be a lambda D of calibration. There's a lambda D of installation. There's a lambda D of engineering. And you sum all those together and there's going to be a lambda D of the human. I'm going to say, okay. Now, if I take the lambda du of the hardware and I add the lambda d of the human, I'm going to get a lambda d total that includes both the hardware and the human. And that's going to be higher than just the random hardware failures. So if I did that, I barely got to my PFD target only looking at random hardware failures. If I include those human failures, I'm going to see that my PFD estimated is going to be less than my PFD target. That's a problem. I didn't achieve my calculated failure measure. My calculated failure measure is less than my target failure measure. That's 11.9.1. Now, what do I do about this problem? Well, it just so happens that we have a list of things that you can do about that in clause 11.9.5. So I'm going to identify the devices that contribute most to the failure measure. So here I know that my transmitter is preventing me from getting to SIL 2. Okay, so which is the device that's causing your problem? Then evaluate the effect of possible improvements. Maybe I could get a more reliable device, a device that has a lower lambda D. I might want to look at common mode, preventing common mode failures. Well, we're 1 out of 1, so we hadn't talked about the beta factor yet. Or these are the keys. Increased diagnostic or proof test coverage, increased redundancy. Actually, that's not the one I wanted to do. So increased redundancy or reduced proof test interval. If you don't meet your SIL target, what are you going to do? You're going to put in redundancy, and you're going to put in, you're going to test more frequently. Did increasing your redundancy or testing more often fix your problem? No. No, it did not. Not at all. So let me explain. Because if all we do is blindly take this lambda, the total lambda, including human failure, and put it in the 1 out of 2 voting arrangement equation, you would think that, hey, now I have achieved a higher PFD. But you did not, because systematic failures, so hear me now and believe me later. Systematic failures have 100% common cause failure. If you do something wrong, you're going to do it wrong every time. That's the definition of systematic. So if I go back here and instead of a single transmitter, I'm going to put in 2 transmitters, because that I need some redundancy to improve my SIL target because I added human failure. Did putting in the second transmitter fix your human failure problem? No, because if your technician miscalibrates this transmitter, they're also going to miscalibrate the new one that you put in. They're going to do the calibration the same way on every device. And if it's wrong, they're going to mess up every device, common cause, 100% of the time. So when it comes to systematic failures, when it comes to human failures, increasing your hardware fault tolerance, changing your voting arrangement does Nothing to improve the situation because the human failure is 100% common cause. Huh. Okay. So the lambda D or the voting arrangement, that didn't help me. But what if I test it more often? So instead of putting in the second transmitter, now instead of once a year, I'm going to do a calibration. I'm going to do a test once every 3 months. Did that fix the problem? Well, if I run my calculation, it did fix the problem. But in reality, did it fix the problem of the human? No, it did not. So basically, we're giving a human being an opportunity to get something wrong once a year. You cannot tell me that if we give that same human being 4 chances a year instead of 1 chance a year to screw it up, that's better. So you're just giving your human being more opportunities to make failure. So if you're trying to address human failures, testing more frequently makes it worse. Adding more redundancy makes it worse. It doesn't fix the problem. Those are the reasons why the standard is so adamant about random hardware failures, because doing better math is not going to fix the problem. All right, so now we're back to kind of looking at clause 11.9.2 in the state that it's going to be after the IEC 61511 committee fixes it. We're going to get rid of that pesky clause K because that just kind of confused people, and we don't want anything that has a human being in it considered for achieving a SIL. So we're going to throw all that stuff out. And now we're back to random hardware failures. Random hardware failures, random hardware failures. Hopefully at this point in time, I've been able to convince you that we don't want to include the failure of the human being in our PFD calculation. But now let me go back to where we started the webinar to begin with. We started the webinar to begin with the fact that, most industrial disasters have a human component to it. So we can't ignore human failures, and we don't ignore human failures, but we don't run calculations on human failures. Where do we deal with human failures? We deal with human failures in clause number 5. So when I go back to clause number 5, what is clause number 5? Clause number 5 is management. So we're going to manage human failures and not run calculations on them. We're going to reduce human failures by putting together a plan to make sure that everyone knows what they're supposed to do, what they're responsible for, when they're supposed to do it, what tools they're supposed to use. So we're going to plan the safety life cycle to make sure that everything gets done and everyone knows what their part in that process is. We're also going to talk about competency. So we're going to make a plan is step 1. Step 2, everybody in that plan needs to be competent to do what they're supposed to do, which means we're going to have formal training, formal mentorship, formal apprenticeship. We're going to do training. We're going to test to make sure that the people understood the training. We're going to qualify them in their work responsibilities by watching them do their work and make sure they do it properly. And we are going to document that. We're going to have a procedure in place to manage the competence that includes documentation of the competence. So we're going to plan everything. We're going to make sure that everybody that's part of that plan is competent, but we're not going to stop there. We're going to do verification, which is clause 7. Clause 7 says we're going to plan for verification. Verification means one person is going to look at the output of a task and verify that it was done correctly. So person A does a SIL verification calc. Person B verifies that calculation to make sure that it was done correctly. And this verification needs to be done for every step, every phase in the SIS safety life cycle in a formal process by someone other than the person who did the work. Okay, so verification, that's great. But we're going to go more. Once we have done our verification, the system is complete, we are going to do clause 13. Clause 13 says that even though competent people did work and it was verified, we're going to do a factory acceptance test. We're going to look at our specs. We're in the factory. We're going to make sure that the system does what it was supposed to do. Then we're going to install it in the field, and we are going to do commissioning. And as a part of commissioning, another group of people are going to look at the installed equipment and make sure that it was installed properly. So commissioning. And no, we're not going to stop there. We're going to do validation. So validation, site acceptance test, the final physical test on the completed system, is another gate that we need to cross to check and make sure that everything was done properly. Okay, so that's on a project by project basis. Those are all the administrative controls, all the human factors, the ways to address and detect human failure. But that's not all. We're not done yet. We're going to go back to clause 5, because when we go back to clause 5, in addition to all the planning that we just went through, we're going to do more. Okay, so we're going to do verification. We're going to do validation. We're going to do commissioning testing. You would think that all of that would be enough. But no, we are also going to do assessments and auditing. So in addition, we're going to do functional safety assessments. What is a functional safety assessment? It's a mini audit that we're going to get an independent team not involved in the project to look at the work that the project team did to make sure that they followed the planning, they used the proper tools, the proper procedures, and their work output is consistent with expectations. So we're going to do functional safety assessments. But we're not going to stop there. We're also going to audit our functional safety process on a regular basis to make sure that all the planning, all the competency is in place. It's being used and it's not degrading over time. So stepping back now into the big picture, the purpose of the webinar was to explain that you don't address human failures by bumping up your failure rates and thinking, well, I used a higher failure rate, so that covers me against human failures. No. We agree, we understand, we know human failures are a problem that we need to consider. But putting them in the PFD calculations, I showed you, not only doesn't fix the problem, it leads you to make bad decisions. It leads you to increase your testing. It leads you to increase your redundancy when those modifications will not make the situation any better. They will not improve the PFD. As a matter of fact, they will make the real PFD even worse because you have basically given the humans more opportunity to create failures, and those human failures are systematic. So 100% common cause. So instead of trying to bump up your failure rate in your PFD calculations, you need administrative controls. You need planning to make sure everybody knows what they're supposed to do. You need competency to make sure everyone is capable of doing what they've been asked to do. We're going to verify every activity that has occurred in the safety life cycle. When the system is complete, we're going to test it at the factory. We're going to check out the installation during the installation and commissioning process. We're going to do validation testing on that final physical system. We're going to do functional safety assessments to make sure we're following our policies and procedures. And we're going to do audits to make sure that our system is always in place, always being used, and will achieve its requirements. So that is the key part of the presentation. That's the big part of the presentation. Again, key message: don't put human failures in your cell verification calcs. Hopefully I've impressed upon you why that is counterproductive. And a note from the 61511 committee: we are getting rid of any reference to including human beings in the cell verification calculations, because we want them to just be random hardware failures. Human failures are addressed in another way. So that's what I've got for the key part of the presentation. I think I have one question to follow up on. So Chris, can you tell me what questions and also if anyone else has any questions, you can start typing them into the chat right now, or if you want to just shout them out. But before that, Chris, what were the questions that were in the chat?
It was just an original one. Can you explain point G again? How does diagnostic test have a human interface?
Okay, so clause G, again, this is something that it was tossed by the committee, because they're like, well, how can a test cause a failure of the device? And how would I put numbers on that? So I'm going to go and I'm going to talk about a test, a very bad test. So let's say I have a vessel. And actually over here, I'm going to have a manway on the vessel. I have a safety instrumented function where my level, if the level goes high, I want to close an inlet valve. And for some reason, the company that built this plant said, you know what I'm going to do? I'm going to take a float type, not level transmitter, level switch. So this is my sensor for my safety instrumented function. And what I'm going to do is I'm going to have basically a type of level switch that is a float on a stick. So as the level goes up, the float will move. So if the level goes up here, and if the level gets high, that will trip a switch, and that will cause the safety function to activate. Okay, so this is my device. When the process is out of service, my float is sitting down here. Now, it's your job to write a test procedure for this sensor. What procedure am I going to write to test this sensor? Well, the only way you can really test this sensor is to fill the vessel up. But filling the vessel up is wasteful and dangerous. So an enterprising engineer said, you know what? Why don't we just open the manway, and then I'm going to go out into the field, or with my hard hat and safety glasses, And I am going to use a calibrated 2x4 to lift the float up. And if I lift the float up and the switch triggers, then that's considered a successful test. Okay, number one, don't do this. This is a horrible test. But you'll see that the action of this operator trying to lift this float up can actually puncture the float. And puncturing the float is a dangerous failure. So for this test that I just drew up on the screen here, the act of testing it, excuse me, the act of testing the device can actually create a failure. And the current version of the standard says, well, you need to account for this. But the standards committee said, no. Where are you going to get data to try to put a frequency of failure on this test? Where are you going to get data to try to put a probability of failure on this test? The real answer is you should not do this. You should instead have your level switch on an external bridle that you can isolate from the process, and you can fill and drain from the top and bottom. And then you can test the device in isolation of the process. And this test with an external bridle won't have the potential failure mode of somebody broke the float with the 2x4. So it's this kind of test that clause G said, hey, testing it can actually destroy the device. But like I said, we in the standards committee said this is too far in the weeds. Nobody's got failure rate data for a test messing up a device, so we're not going to include it in the calculations anymore. Okay, Chris, I think there were a couple of follow-up questions that happened in the chat.
Yeah. Are there any good databases or experience information that quantifies operator actions to an alarm?
Yes. So the probability that an operator will respond to an alarm is a function of a lot of things: training, stress, the amount of conflicting information. The book. Let me see if I can find it on the internet real quick. Amazon.com. I'm not promoting Amazon. They just have a lot of books. I think it's Gertman and Blackman. Yep, that's the one. I highly recommend this book here, Human Reliability and Safety Analysis Data Handbook. It's going to have tons of tables that will give you different failure rates for different situations, different stress factors. Also in the human reliability, in this book, they discuss something called the Sandia recovery model. So the Sandia recovery model, not only does it give you probabilities of human failure, it will give you it'll give you charts that will give you the probability of human failure as a function of time. So this book, it's, I don't know how many pages, probably a couple 300 pages, just completely filled with data tables, charts, and graphs, in addition to an explanation, and it's nothing but human reliability. So, for instance, there's even a table in the book that says, if you send an operator to the field to open a valve, in a manifold, what's the probability that they'll pick the wrong valve? And there are numbers that say, well, if the numbers all, or if the valves all look the same, if they're all the same size, if they're different sizes, if they're tagged differently, if they have different color tags, they will give you probabilities for every one of those combinations and permutations. So I highly, highly recommend this book. 90% of what I know about human reliability, I learned out of this book. All right, next question. I see they're rolling in.
Yep. Wouldn't proof testing help in identifying or reducing engineering or installation errors and eat up a slice of the PFD for humans in a way?
Um, yeah. So I understand the okay, so let me come back and say, in terms of human failure, and you know they talk about it in this human reliability book. There is a chance that if you make a mistake, you will realize you made a mistake and correct it. It's the probability of you detecting your own mistake and correcting it, again, is complex, but it's a very low probability. Whereas it's a lot easier for somebody else to detect that you made a failure and uh, point that out. And so if your job is to look for someone else's failures, you have a much better chance than if you made the failure yourself. And that's the key concept that we're going for in functional safety assessments, in audits, in commissioning. So the probability of an installation error being detected during commissioning is actually relatively high because you've got an independent third person who wasn't involved in the installation checking it out to make sure. But so I absolutely agree conceptually that, hey, commissioning is probably going to detect a systematic failure that occurred during the engineering phase. But I'm still not on board with putting a engineering systematic failure rate in our calculation. I'm recognizing it and I'm saying, hey, commissioning needs to be done. FAT needs to be done. SAT needs to be done. And we're hoping that those tasks done by competent people are going to catch any errors that occur earlier in the life cycle. But yeah, I'm still not a fan of putting it into the calculation. And in the calculation, the thing that is never going to get caught is something like, and it's why I focus when I teach this on the technician miscalibrating the device. No one is going to go back after the technician and check to see that they calibrated the device correctly. So that one, it's going to be systematic. It's not going to get caught.
Okay. As per definition, SIS could use any combination of sensors. Can
Yes.
we have a voted combination of a transmitter and a switch? For example, 2 out of 2 radar level transmitter and a tuning fork switch. Do the sensors have to be apple to apple comparable in terms of accuracy and speed of response?
Uh, no. You're allowed to mix and match all you want. So if you look at the sensor subsystem of a SIL verification calculation, um, and here, let's say we've got, I ran the calculation in a 1 out of 2 vote, but let's say I have a generic displacement type level transmitter, and I have 2 of the devices, and let's say I want to run them in a 1 out of 2 vote, run my calculations there, and it's going to calculate all your stuff. Fine. Now, what if instead of a 1 out of 2 vote, I had a 2 out of 3 vote where I've got my And it's very common to see a tuning fork switch being the second or third device, because a tuning fork switch, we can kind of ad hoc kind of pipe that into a pipe column, to fix a design problem, shall we say. It's something that you can jury rig after the fact. The problem with that, and let me start out by saying it's absolutely unequivocally acceptable to do that. You can even have a guided wave radar, a displacer, and a tuning fork switch all be part of a 2 out of 3 vote. The problem with that is my calculation just got more complicated. So what you would have to do is, instead of saying I've got a 2 out of 3 vote. So if I say I've got a 2 out of 3 vote, it's assuming I've got a 2 out of 3 vote of generic displacement high trip level transmitters. If you have 3 different devices, things got more complicated. So instead, what you're going to need to do is you're going to need to run a fault tree. So here, you'll see that I've got a fault tree of a pressure temperature compensated flow. So I've got my pressure transmitter, I've got my temperature transmitter, I've got my flow transmitter. All of them, well, I put the same failure rate in here just to save myself time. But in reality, all these devices would have different failure rates. So you could put in, if you had displacer level is one event, guided wave radar is another event, switch is another event, and then you make your gate a voter gate, 2 out of 3 voter gate, and then it will run that calculation for you. And then back in Arbor, you link to this fault tree. Instead of having a native calculation, you basically tell Arbor, go to this fault tree to calculate the PFD. So absolutely, you're allowed to do it. Not a problem whatsoever. You just made your SIL verification calculations a little bit more complicated, but if you're in the Connexus framework, just run a fault tree and link it into your Vertigo study. Next question.
Okay, if the technician during an I/O card replacement activity accidentally caused a SIS trip, is that a random failure or a systemic failure?
Okay, so if a technician doing a replacement of a card
I/O card.
causes a spurious trip, is that random or is that systematic? Well, it appears random, but it is systematic. Let me explain. So basically, before the technician tried to change out the IO card, that technician had a mental procedure that they were going to follow to do that replacement. So they were following their mental procedure for how to do that replacement, and that mental procedure will systematically always trip the plant out. Now, after that technician tripped the plant out, they changed their mental model to a new model, a new procedure that's not going to trip the plant out. But the reason it would be systematic is before that technician created that failure, that technician could have been sent to any PLC in the plant and would have systematically caused that trip. It's just that after they caused the trip, now there was a paradigm shift in the procedure that they're using. But their mental model that they used that caused that failure was systematic. It would have caused that failure every time you repeat that procedure on any system. That would have happened. It's tricky because you can understand why you would think to call it a random failure, because once they do it once, they're never going to repeat it. But for that first time, it absolutely is systematic. Thanks, everyone. I appreciate your time. I appreciate your attention. Yeah, keep the questions coming, and there's going to be at least one of these every month. So keep coming back for more.